So how does it, all of you have breakdown of the power, right? So you have one power during takeoff and power for due to skin friction drag and due to induced drag for cruise. How do you think the three different powers are going to suggest how you can improve your design? Well, let me first ask, what if you calculated a takeoff power much smaller than the combined cruise power? What do you think you can do? What do you think, how do you think you can take advantage of that? Yes?
Like rotors, you could size, like take off, you could size them down.
Exactly, you can size your rotor down, right? That means like maybe you have a lot of power to take off with a small rotor that wouldn't penalize your cruise performance. But you designed a big rotor, right? So you can shrink your rotor down, and you still have enough power to take off. But the cruise design is going to be much easier because of the smaller rotor. Thanks, that's good. Now, how about the power breakdown during cruise? Right, I know like a lot of you optimize the altitude according to the power for skin friction and the induced power, right? So there is usually a minimum at some altitude. Now, let me ask a question. How does that minimum, how do you think that minimum is going to change if you shrink your chord length without changing your span? Yes?
You feel like going through the same amount of skin friction drag, but less induced drag?
That's actually, maybe let me ask again. So without changing the span, so B is the same, but shrink your chord length. Induced drag is, how if you fix the span, right, how does the induced drag change as you shrink the chord length? Doesn't change, right? The induced drag is just a function of the span, all right? So induced drag doesn't change. How about skin friction drag? It decreases, right? Because your area got decreased. So if you guys remember, like altitude and drag, as you increase in altitude, right? The let me say the induced drag goes up. So induced drag goes up, and the other component, skin friction drag goes down, right? So something like that. I think all the analysis I've seen had either tables or plot like that. So that's very good. The thing is that as you decrease your chord length, this guy would decrease, right? Okay, so why don't we just use an infinitesimally small chord length? Yes?
Fast.
That's what?
That's like you have like keeping the chord length smaller. You need to like go faster to get the same amount of lift.
It has to go faster to get the same amount of lift. Actually, that's quite similar to the answer I'm going to give, is that especially at lower speed, having a small chord length may require you to have a unfeasibly high lift coefficient. Right? This is when we are now getting close to starting to design airfoils, right? So we know like how much lift coefficient you can achieve really depends on what airfoils you have. So it is always reasonable trying to keep the same span and just having a small and smaller chord length, having a high aspect ratio wing. There are two penalties. One is throttle penalty. So that's going to be the equation we supply to you. So if you decrease the chord length, right, you get the wing smaller, but the smaller wing is actually going to be heavier. All right, so that's something we probably want to start considering this week, is that as you keep your span, you change your chord length, right? How is that going to change your weight? And the weight, again, is going to, so essentially, if you shift the skin friction down by decreasing the chord, the induced drag is going to increase, right? Because the weight is increased. Induced drag is proportional to the square of the weight. All right, so that's one trade-off. Another trade-off is as you decrease the skin friction drag by decreasing the chord, at some point you're going to hit a barrier, you're going to hit a constraint. That is, at the lowest speed at which you are relying on wing to provide lift, okay, you have to achieve the CL, right? You cannot, so at that point, at some point, you are going to require an infeasibly high lift coefficient at the slowest speed you are cruising. Okay, I know like all of you are doing this helicopter versus helicopter takeoff. So the slowest speed you're flying at an airplane mode usually, it basically is the highest speed, right? You can go at helicopter mode. And for helicopters, we're not going to the design of helicopter rotors, but one thing is that we can assume by a helicopter it's very difficult to go faster than a third of the speed of sound. Basically, at that point, even if your rotor tip spins at the speed of sound in the forward sweep, the backward is going to be only a third of the velocity at the tip. And a huge portion of the backward swiping phase is at a negative speed. So essentially, the blade is going back, but the airplane is going forward. So a large part of it is going at negative speed. So only the tip provides any lift, and even that, the lift is much smaller because the speed is only a third. And the advancing side is already going at Mach 1. So this is basically extremely difficult place to fly as a helicopter already at a third of the speed of sound. So it's let's without going into the design of the rotors, let's just assume you are capped at a third of the speed of sound in helicopter mode. All right. Okay. Makes sense. So you have to fly at airplane mode, starting at a third of the speed of sound, and you cannot have a chord too small for you to fly at airplane mode at that speed. Okay. Any questions on that? Yeah? No? Okay. Another variable you can vary independently is the span, right? Okay, so span, I think increasing span is a little bit, increasing span actually changes two things, right? One is it increases the area, so it kind of pushes this up, okay? At the same time, it decreases the induced drag by pushing this down. So this is another trade-off you can make on your design. So it's going to make this picture also different. And at some point, the decrease in induced drag in increasing your span is going to slow down more and more, because the further you increase your span, the more weight you're going to be putting onto the airplane, right? A higher span wing weighs more. So on one hand, you're actually decreasing the induced drag, but by increasing B, but then at the same time, you are increasing the weight of the airplane. You are increasing W. So at some point, the additional gain you get by increasing span just gets diminished more and more. So that's another thing you should consider when you're designing the airplane. So essentially, today we talked about how do you change the chord and change the span, right? And then you can redo this calculation and figure out how big the wing and what's the shape of your wing should really be. All right, make sense? So this is probably the first thing we are going to do, okay, in the design. And the second thing is to do a balance and the stability analysis to figure out, okay, now I have the shape of the wing, I know the chord, right? I know the span. Where should I put it relative to the fuselage? And how big of a tail do I need? And how long the fuselage has to be, so that the tail has enough moments to balance it. All right, so these are, I think, the two primary things we are going to be doing this week. And once you decide on both, it's actually you have enough knowledge to design an airfoil, right? You know how much lift you have to provide, and at transonic or supersonic conditions, right? You have different requirements. So basically, the lift coefficient constrains you from the low speed side, and the drag constrains you from the high speed side. So these two are going to combine and allow you to now start designing airfoils. Okay, so wing plane form, stability, and airfoil are the three major things we'll be doing. Basically, we want to get the initial design of this, all of these three, right? By the draft project is due, which is I think next Monday, right?